Hello. So today we are doing a problem um, called binary tree longest consecutive sequence. So basically, the problem is we get binary tree. So binary tree like the following, where we have 1 here, 2 and 3, and then we have 2, 4. So 1 has 2 children, 2 and 3 has 2 children, 2 and 4, and 3 has, and 4 has child 5, right? So we have this binary tree here, and the longest consecutive branch is basically a branch where the parent value, let's say, is x, then the child value should be x plus 1. So, and we need to find the longest one that verifies this property. So, for example, here 1 has child 2, so that verifies this property. And so we can say we have one that is 2, that we have a branch that has length 2. 1 plus, for 1 and 3, that's not the case. For 3 and 2, it's not a consecutive branch because 3 is bigger than 2. But 3, 4, 5, that's a consecutive branch. 3 plus 1 is 4, 4 plus 1 is 5. And so we can say that the longest consecutive branch in this case is 3, 4, 5. So our longest consecutive branch is 3, 4, 5. And so in this case, so in this case, it's the length is 4, it's 3. Just to visualize this, I'm going to use a tool I have here. So let's import. And then we need to do deserialize. Let's say, so the tree we have is 1, and 1 has child null, and then null has child. And then we have 3, which has 2 and 4. We have null. And we have 5 as a left child. Yep, so we need a null here. Okay, 1 second. Let me take another one that exists already. So something like this. This is the tree we want. Okay, so let's see what this tree looks like. So the tree looks like this here. So we have 1, and then 3, 2, 4, 5. So, yep, so it's a little bit like this. Let's ignore this for a while. So it's like this. So this is the tree we are working with. And so the longest consecutive branch is 3, 4, 5. So let's see how we can solve this problem. So this can be solved with DFS. So what we can do is go using DFS, traverse the tree, and keep a counter of the consecutive like children that verify the property, this property here, and each time do the max, and at the end return the overall max of the entire thing. So that means we can do something like let's see, let's call it consecutive branch. So it would be longest consecutive branch. And then we need to have a root. And so we are going to define DFS, so we need a node. And we need the value of the parent. So each time we go to a node, we need to know the value of its parent. So at 3, we need to know the value of 1. And so we need to pass the parent value. And also, for example, at 3 here, we need to know that we have for what's above us, we have the count of the longest consecutive branch is 1. And at 4, we need to know that it's 1. At 5, we need to know that it's 2, which is 3 and 4. And so we need to pass it like this. Now, if we get here and it's at the end, so the value of the node is null, then we need to just return the count, right? We are done, so just return count. Otherwise, then we have two cases: either that the value of the current node is not equal to the current value of +1, so this property is not does not occur here, and so in that case we need to resume and try to find another longest one, and so we need to do the max of the current count and do a DFS on node.left. And the count value is node.val. And the count is just, this time it's 1 because the property is no longer verified, so we need to restart looking again. So for example, in this case, we did that for 1. When traversed 1, we have the count is 1. But when we get to 3, 3 is not equal to 1 plus 1. And so we need to start again. And so the count starts to be 1 for 3. And then at 4, then we add 1. So that would mean here we pass just 1 as the count. And we need to do also a DFS on node right. And value is still 1. Now, if that, so we need to return that. Now, if the node val is equal to the parent val plus 1, so the property is still verified, it still works, then in that case, we need to do count plus 1 instead. So for example, at 4 here, we need to do 1 plus 1 so that it counts as 2, because 3 and 4 is the longest branch now. And at 5, we need to count 2 plus 1, because the longest branch is 3, 4, 5. And so that would be count plus 1 here, and we can return that. Now let's run this. So our example here should return true. So let's run that on it. So let's say, let me just put this here. So we can say assert. Let's create our solution here. And let's create our, this is just, this tree tool is just a utility that creates a node out of this list. So yeah, not a, okay, so this here should be equal to 3. So let's see if this works. Okay, so it seems like we have a problem. What did this return? Let's print it. So yeah, we didn't return the result at the end here. So we should do DFS on root. And just as a way to start, we can say parent val minus 1 so that the count is 0, so that it's always the case that this node val is equal to parent val plus 1, just as a starting point. And then one edge case that we need to handle is if the root is null. So in that case, we need to just return 0. Yeah, so now it passes, it works. So this is basically, we just do DFS, and if the value of the node is equal to plus 1, then we count plus 1, otherwise we start again. Now let's look at, we can make this solution shorter. So let's try a couple of things here. So actually, we don't need to specialize this case. We can just say that our new count here is equal to, so it's equal to count plus 1 if this is equal to node val equal to parent val plus 1. Otherwise, it's just one that we used here. And we can just avoid specializing here and just do new count and new count instead. And this does the exact same thing. And we can go even further. So here we are applying DFS to node.left and node.right, but the rest of the parameters are the same. And so we can take advantage of Python's max function and instead just use one declaration, and let's call this a kid, which is our child. And then for child is either node left or node right. And this should also pass. Also, another thing is we can not avoid explicitly doing this. So at this point, it's already readable and quite short. So I would say this is good enough, but we can even make it shorter just for fun. So we can do, so this is if node, and otherwise we can just return 0, right? Yeah, so first let's just take this one also. We can put it here. And so now it's a one-liner. It's a little bit long, but yep. So if not node, we need to return count actually. Okay, and same thing here. We need to do this if root, else we can return 0. And this is a lot shorter. It's less readable, but yeah. So that's it for now. See you next time. Bye.